Ever wanted to build your very own iris detection model? Well, in this video, we're going to be doing exactly that using Python and deep learning. You'll be able to take a frame from your camera and use it to track your eyes. Let's jump into it. What's happening, guys? My name's Nicholas Renard, and in this video we're going to be doing iris tracking or iris detection. We're going to be using deep learning and Python to be able to train a custom model from scratch using the Keras sequential API to be able to track our eyes. Now this has a bunch of use cases. Let's say, for example, you wanted to see where a pilot or a driver or an engineer is looking at in terms of instrumentation. You could also use it to see where people's attention are being directed into. There are a ton of use cases for this. In this video, we're going to be taking a look at quite a fair bit of stuff, but specifically we're going to be getting set up. We're going to be loading in our data using the Keras dataset API or the Tensorflow dataset API. We're then going to build our own deep neural network and train it. We'll then evaluate it, so we'll take a look at how it's actually performed. And last but not least, we'll test it out in real time just to make sure it is working as well as we say it is. Ready to do it? Let's get into it. Hey Nick, have you ever looked at your pupils? How am I meant to look at my pupils, man? Anyway, you think you can use ML to track your eyes or irises? Just casually changing the conversation, are we? Anyway, yeah, we can. First things first, let's run through how it's going to work and get our environment set up. Off to the breakdown board? Off to the breakdown board. Welcome on back to the breakdown board. So as per usual, we're going to be doing a high level sort of like bird's eye overview of what it is that we're going to be building in this video. So first things first, I've actually gone ahead and annotated a ton of data to be able to do this. So I actually collected images using the same technique that we used in the face detection module. And what we're going to be doing is we're going to be loading this in using the TensorFlow datasets API. Oh, pen is not working. So we're going to be doing that over there. Now, we'll be using the list files function, so what I've drawn over there, to be able to load it in. And as per usual, we're going to be running through our McDonald's McShabbat pipeline. So remember, there's a couple of key steps that you want to use when you're using the TensorFlow dataset or TensorFlow datasets API. So there's map, and that's the M in McShabbat. There's cache, and this caches our data. Then there is shuffle, and this shuffles it up to ensure that we're not just looking at one sort of stream of data. And then we've got batch and prefetch. So map is what effectively is used to actually read in the data. So we use list files to be able to list all the files in the directory. So think of this as going, hey, show me every single file in this directory, and then we're going to be able to do something with it. The way that we do something with it is using the map function. We're then going to cache our data. So this means that it's going to be stored in memory, that it's going to be a little bit more readily accessible. We'll shuffle it up. So again, we're not going to be processing one stream of data, and this will ensure that we get much better results. We are then going to batch it up, so we're going to be able to pass through mini batches to our final deep learning model, and we're going to prefetch it. So this helps alleviate any bottlenecks. Now, in terms of the data that we're going to be using, we're actually going to be loading these up using OpenCV. So we'll actually have an image, and this image will be 450 pixels by 450 pixels wide. These were originally collected using my webcam, and again, I'm going to give you the data pipeline and collect this data yourself if you want to do a custom model. But what it effectively is a picture of myself, and I've gone and annotated my left eye iris and my right eye iris. I think that's the right way to pronounce it. And so what we'll effectively have inside of this model, so let's actually finish the drawing of myself. So let's say that's my eye there, it's my ear there, it's my big smile, spiky hair, even though I've got none at the moment. What I've actually gone and annotated is the iris in one picture, or the iris for each picture for both my left and my right eye. So you've actually got a JSON annotation which represents each one of those eyes. I also did a classification annotation, but we're not actually going to use it in this case because it's just going to be a little bit faster. So just know that you're going to have one image, and for each image you're going to have a corresponding annotation. Now that annotation is in JSON format, and we've effectively got an X and Y coordinate for my left eye and an X and Y coordinate for my right eye. So if you were to collect this yourself, it'd be done the exact same way. The way that I annotated it is using a library called label me. And this is the exact same library that we used in the face detection video. So if you want to check that out, by all means do it. Now, on to our deep learning. So how is it exactly that we're going to be building up this model? Well, we're going to take advantage of one of the most unique features inside of Keras. We're going to take a pre-built image classification model and add it on to our neural network. So we're actually going to use this as what is referred to as a backbone. Now, when we typically refer to a backbone, it's going to be the part of the neural network that does the heavy lifting. In this case, it's no different. We're actually going to be using a ResNet base architecture, and we're just going to finally add on the final layers that we actually need to be able to get our specific outputs. So we'll actually have ResNet over here, and this is going to be using a whole heap of CNN layers and max pooling layers as well. So this is a best practice architecture, that particular ResNet model. All we need to do is add on a bunch of layers towards the end to tell it that, hey, we actually want this type of output, not necessarily a classification model. So we're actually going to fine tune and stack on a couple of layers. My pen has disappeared. Stack on a couple of layers, as you can see here, to tell us, hey, give us 4 coordinates to be able to represent the X and Y coordinates for our left eye and our right eye. So what we'd effectively have is, or what we're going to get out of this particular neural network is the X coordinate for our left eye, the Y coordinate for our left eye, the X coordinate for our right eye, and the Y coordinate for our right eye. So you effectively just get 4 different values. Now these are going to be normalized, so they're going to be divided by the size of the image, so they're going to be between 0 and 1. What we can then do is scale them back up depending on what our size of our image is. So this just helps our neural network train a little bit faster. But effectively, it is a regression problem. Cool, so once we've actually gone and trained that neural network, and for the loss function there, we are going to be using MSE, so mean squared error, because we want our coordinates to be as close as possible to the actual coordinate. So we're going to try to minimize that distance. Once we've gone and trained that deep neural network, we are then going to be able to make predictions. So in order to make predictions, we're actually going to take our 450 by 450 pixel model or image. We're going to make that a little bit smaller, so it's going to become 250 by 250 pixels, and then we're going to output those coordinates. So we'll have X, Y, X, Y, and we'll actually be able to use that for real-time detection. So in order to do our real-time detection, we're going to have a Keras, or actually an OpenCV frame, and that will be just connected to our webcam. So this is the true advantage of actually doing it with something like OpenCV. We can actually go and test our model out in real time, because evaluation is great, but you always want to try to test it out on data that it's actually going to see. So let's say that this is a webcam image of myself. We'll actually be able to go and make those detections to see where our left eye is and where our right eye is. So we'll actually be able to get those coordinates out, and we'll be able to render it to the computer screen in real time using OpenCV. Ready to do it? Let's kick off our coding.
Okay, so we've had a chat to our client. Now, the first thing that we're going to be needing to do in order to get our iris tracking model or iris estimation model up and running is to install and set up some dependencies. So there are 4 different dependencies that we're going to need for this tutorial. That doesn't include the sets of dependencies that you'd probably need for the data collection side of things, but we'll talk about that a little bit more once we get to stage 2. So the first command that we're going to run is !pip install TensorFlow, TensorFlow-GPU, OpenCV-Python, and Matplotlib. And as per usual, all the code for this particular tutorial is going to be available on GitHub. So if you just go to, let me zoom in on that, nickknockknack or github.com/nickknockknack/iris detection, you're going to be able to download this notebook, so the one that we're going through right now, and the data collection notebook, which I'll talk about in a sec. So again, it's just a Git clone, and if you're not familiar with how to pick up these particular notebooks or get them up and working, do check out the deep learning beginner tutorial, because I go through it in a ton of detail, how to get your environment set up, how to start running through a notebook. Okay, but for now, let's assume we've got our environment set up. We're all good to go. So we're going to go on ahead and run this command here. And this should install TensorFlow. So TensorFlow is going to be used in order to build our deep learning model. OpenCV is going to be used to capture our frames at the end. And Matplotlib is going to be used for both rendering our images in real time, but also we're going to be using it when we go and view our loss metrics and evaluate the performance of our model. Okay, so let's just double check. So it looks like we don't have any errors there. So it looks like everything's already installed and looking pretty good. Now, just for reference, because a lot of people like to know, so if we go and take a look at the versions of stuff that I'm using, so in terms of TensorFlow, I think it's 2.8.0. Yep, so you can see TensorFlow 2.8.0 and TensorFlow GPU 2.8.0. GPU is optional, but in this particular case, I think it is really, really important that you do have a GPU because we're training quite a large model. Okay, cool. That's TensorFlow. And again, in the Deep Learning for Beginners tutorial, we go through how to install TensorFlow. So just bear that in mind. Okay, so then we got to import some stuff. So first up, we are going to import OS. So you've probably seen me use OS a bunch of times. So typically we're writing in os.path.join, and this allows us to just more easily concatenate different file paths together and traverse through directories if we need to. Second thing that we are importing is CV2. So this is importing OpenCV. So import CV2 brings in OpenCV, and we're going to be using that for capturing frames, working with different components of data. Looks like we've got to import it twice there. Next line is importing TensorFlow. So TensorFlow is going to give us our deep learning library. So import TensorFlow as TF, and we're typically going to be, or mainly going to be using the Keras API for that. Import JSON. We're going to be using JSON to load in our labels, and I'll talk a little bit about data in a second. We're importing NumPy. NumPy just helps us when we're working with different types of arrays. So we've got import NumPy as NP. We're then importing matplotlib. So from matplotlib, import pyplot as PLT. So plt.imshow allows you to go, so the command is plt.imshow. That actually allows you to go and render images to your screen. And it also, the other thing that we typically use is plt.plot. So that actually allows you to plot out a whole bunch of stuff, and you'll see me using that a little bit later in order to visualize our loss metrics. But for now, let's go on ahead and import those dependencies. And again, it's just a shift enter on each one of these cells to go and run them. Then, because I am using a GPU on this machine, you would have seen me use this a bunch of times, we are going to go and set the GPU memory consumption growth. So we're going to limit that. And effectively, what we are writing is GPUs equals tf.config.experimental.list_physical devices. And we're grabbing all of our GPUs. And this line over here is effectively setting our memory growth equal to true. So this basically caps how much memory that TensorFlow will use rather than blowing out and grabbing all of it, because that's what it will do otherwise. So we're going to loop through every GPU in this line here, and we're going to set memory growth equal to true. Again, you've seen me do this probably a bunch of times. So if we take a look at GPUs, you can see that we've got one GPU there. If you don't see a GPU here, that means that you probably haven't configured TensorFlow GPU correctly. So again, we go through that in the beginner tutorial, how to install CUDA, how to install CUDNN for deep learning. Okay, that's our first section done. So we've gone and let's just, no, that's all clean. So we've gone and done a couple of things. So we went and installed a bunch of dependencies. We then went and took a look at versions. I gave you a bit of an explanation as to what the lines of code that we're going to use. Imported a bunch of things. So 1, 2, 3, 4, 5, 6 different imports. So OS, CV2, which is OpenCV, TensorFlow, JSON, NumPy, and matplotlib. And then we went and set our GPU memory consumption growth and limited that. Okay, let's jump back on over to our client and see what's next.
Now that we're all set up, what's next? We need data. Ah, yes. It's like the famous quote from Kendrick Lamar. While you're only babysitting 2 or 3 shots, let me show you how to turn it up a notch. First you get a swimming pool for the data, then you dive in it. Kendrick said that. Yep, I'll take your word for it. So yeah, we need data. In this case, we've already got the images and Keypoint annotations prepared, so it's just a matter of getting them into our deep learning and data pipeline. Cool, but this could be done with any data set, right? Yep, I'll actually show you how to collect and annotate as well, just in case you want to go and collect this data yourself.
Alrighty, so we're now up to part 2, loading in our data. Now, we've got a ton of images and annotations that we're going to be able to work with. Now, I did try to upload this data set to GitHub for you, but it was 600 megabytes in size, so I'm probably going to have to work out how to actually go and do that. I know GitHub's got a large file extension, so I just need to go and work out how to do that. But I'm going to show you the data set, and I'll show you how to create your own if you want to go and do this yourself. So if I jump in to my root folder, so I'm currently working in a folder called eye tracking. I've got this folder over here called org data, and this is just augmented data. So again, if you've seen the face detection tutorial, you probably would have seen this folder yourselves. So if I open this up, I've got 3 different partitions. So train, let me zoom in more so you can see it. So train, test, and val. So training is going to be the data that we use to train our model. Validation is going to be the data to validate whilst we're training. And this influences our design decisions for our deep learning model. And test is what we use to finally evaluate or test out our model on in terms of its performance. Okay, so what we first up want to do is let me actually just show you what we're working with here. What we're working with. So if we're going to train, we've got two folders and we've got one folder called images, one folder called labels. Wow, it looks a bit blurry. That's a bit better. So if we jump into images, you can see it's a bunch of images of myself looking all a little bit disheveled, trying to make this tutorial. So this took quite a fair bit of time to actually get up and running. But you can see it's a bunch of images. Now, I didn't actually collect, this is 7,680 images. I didn't actually collect every single one of these images. What I did is I used the same image collection pipeline that we used in the face detection model. I then labeled it using label me, but rather than doing bounding box annotation, I actually did keypoint annotation. And I'll show you an example of how to do that in a second. So you can see I've got a bunch of images, which we ran through an augmentation pipeline. And our labels. Now, this is the really important bit that I wanted to show you. So you probably would have seen the annotations previously for the face detection model. For keypoint detection, it's different. So here we've got the name of the image, which is perfectly fine. We're not really going to use that. We've got the class of the image, and this is whether or not the eyes are visible or not, or the irises are visible or not. So if it says 1, that means they are visible. And then we've got our key points. These are the really, really important bits. So I can't remember which order I saved these in, but I believe it's X, Y, X, Y. So this will be X1, Y1 for our left eye, X1, or X2, Y2 for our right eye. So it's effectively, well, X1, Y1, X1, Y1, and then they're just for different eyes. So these annotations actually represent the coordinates of our eyes with respect to the image. Now, how we actually get these coordinates is done, again, using the labeling library called Label Me. So let's actually take a look at what that might look like. Let's actually grab an image and do it as well. So let's grab one out of train. And I'm just going to put it in the root folder, and let's open up a new command prompt. So I'm going to go into my D drive, CD YouTube, CD, 15, activate my environment. And again, I've shown how to set up these environments in the beginner tutorial. So if you need to understand what I'm doing right now or how to actually customize and activate these environments, please do check out the beginner's tutorial because we definitely do go through it. All right. What did I do there? iTrack script activate. Okay, so let's go on ahead and open up Label Me. So in order to install Label Me, it's just pip install Label Me. And again, we went through this in the face detection tutorial. So it's probably worthwhile if you're going to give this tutorial a crack, take a look at that one first so you'll get a better idea. But all of the code that you're going to need is inside of this data collection video or data collection notebook. So if we go and start out Label Me, just by running Label Me, this is what's going to open up, right? And then what we can do is just hit open directory over here. So you can see open dir. Let me zoom in. If I do that and then select that folder, I should only have one image in there. Do we have one image? We do. Looks like it's free. Okay, there we go. So that's gone and open. So you can see it's a picture of myself in the background. Then in order to annotate these images, so in the face detection video, we went and created rectangles. So you can see that there, right? Create rectangle. We are not going to do that for this video. We are going to go and hit create point. So this actually allows you to do a key point annotation. So rather than actually drawing a whole square, we're just going to put a dot on our iris and we might say left eye or label it left eye. And then for our other eye, we're going to do right eye. Boom. Now, in terms of the specific class names that the code is looking for, let me actually just show you that. I can't remember what I called it. We are looking for, so it's capitalized. So it's right eye with caps and then left eye with caps. So these are the class names that you should be putting. So let's go and delete that because we don't want that. So let's deselect those. So what we do is do that and it would be, what is that? Left eye. And then do the other one, right eye. And you'd effectively just go and do that for all of the images that you've gone and collected. Now, what you're going to get out of this, so let's save our annotation. So you can see it's going to be saved as the exact same name as the image, but it's just going to have a JSON extension. So let me zoom in there so you can see that. Presto. Save. And then if we actually go and take a look at that, this is what the raw annotation at a label me looks like. So we're going to get the set of coordinates for our left eye, and you can see that this is not normalized. So when we actually go and pre-process it, we go and normalize it. So, and by normalize, we're just dividing by the width and the height of the image. So that's the label for our left eye. This is the label for our right eye. And then we could delete these one or delete that group ID. We don't need that. But this gives us our coordinates. Now, in terms of how I set this up originally to actually go and annotate, you'd actually go and create a folder called data. It's pretty much the exact same way that we did it for our face detection tutorial. So if I actually show you what that data set looked like originally, so I had a folder called data, and then this was inside of my root directory. Inside of images, we had all of our images. Inside of labels, we had all of our labels. And then exactly the same as we did in the face detection tutorial, I just went and partitioned it out into train, test, and val. So that would get you, if we go and take a look at our data collection code, that would get you up to this point in the tutorial. So if you take a look, the first part of the data collection video is going to help you collect videos or collect images, and it's going to store them inside of the data folder. And again, inside of that, you need to have an images folder. And then when you go and create the data set, you'll be able, then you need to annotate and then partition. So collect, annotate, partition, and then from here, it's pretty much all set for you. So this will move the labels into their respective data augmentation folders. This will run your augmentation pipeline, and it will be all good to go. And you will effectively be at the state that we are at now. So again, if you want a more detailed video on how to actually do the annotation and prepare this data set, do let me know. But this sort of is going to give you the rough outline as to how to go on ahead and do key point tracking in general. Okay, that's a little bit on data. Let's actually go on ahead and load up our data now. So in order to load our data, first thing that we need to do is define a function to load our images. Now we've created a function called load_image. So that is DEF for defining a new function, load_image. And then to that, we are going to be passing through the image path. That's what this X is going to represent. We then pass that to tf.io.read_file. So the file path gets passed to that. We then get a byte image representation back, and then we take that and pass it to tf.io.decodejpg. You can see that that is being passed to there, and we get our image back, and then we're returning that back. So if we go and run that, what we're then going to do is run it through the Mxshabat pipeline. So the first thing that we're going to go on ahead and do is load up all of our file paths. So again, we went through this in a little bit more detail in the face detection video, but I'm going to explain it again anyway. So we are going to store all of our image paths initially inside of a variable called train_images. To get those image paths, we are going to write tf.data.dataset.list files. So this has the function of looking inside of a folder and showing you all the files that match a certain wildcard search. Now we are searching for anything which ends in .jpg, and we're specifically looking inside of the org data folder, inside of train, and inside of images. So if we go and take a look at that, so we're going inside of this folder, inside of train, and inside of images, and there are a ton of images in there. So I think I showed you that just a second ago. With something like 7,000 plus images. Cool. And then let's jump back. This does lag a little bit when it tries to show all of the different images. Let's just delete that image and annotation out of there because it's looking a little bit messy. And again, my OCD is kicking in, so I don't want these two here. Much cleaner. Beautiful. Okay, so we are loading in our file paths. So in order to do that, you pass through the full file path that you want and then the wildcard search. I'm passing through star.jpg and I'm setting shuffle equal to false. This is really important because we're going to marry up the annotations with these images in a second. Then what we're doing is so right now from this particular line, all we'd be getting back is the actual name or the file path, right? So if I run that line and type in train.asnumpyiterator.next, so this actually allows me to get one example out of this data pipeline. All I'm getting back is a file path. So that's just a file path. It's not the actual image itself. If I then go and run this second line, this is going to add in a second step to our data pipeline, right? So I'm now going and running train_images and I'm running .map. What map does is it applies a specific function to every single instance inside of that data pipeline. Now the instances are all of our label paths. So exactly what you're seeing here, right? So what it's effectively going to be doing is it's going to be taking this and passing it through to this load image function, which is going to then return our image. So it almost does like that type of transformation. So What we're then going to do is we're going to overwrite the train underscore images variable with our new images. So if we go and run these two now, what we're getting back is an image, right? So that's actually an image there. So if we wanted to, we could type in plot.imshow, and you can see we're rendering our image. So rather than just having the file path, we've now got our image. Now the next line that we're going to run is we're going to resize our image to be 250 by 250 pixels. So if we take a look at the size of this image right now, let's type in .shape. You can see it's 450 by 450 by 3. If we now go and add this line to our data pipeline, it's going to resize it by using tf.image.resize, and we're going to resize it to be 250 by 250 pixels. So again, pretty much the same as what we did in this line, but here we're using a lambda function rather than just our raw function that we defined over here. So we've now got train underscore images.map. Again, we're using the map function or map method. We are then typing in lambda x and then a colon, and then what we want to do for every example inside of our data pipeline, which is resize. So tf.image.resize, we pass through the image because that's what we had from over here. And then we're resizing it to be 250 pixels by 250 pixels. So if we go and take a look at this now, boom, we're now getting back images that are 250 pixels by 250 pixels. And the reason that we're doing this is we're going to be effectively reducing the amount of data that we need to process so we can bump up our batch sizes when we're doing our deep learning. So if we go and take a look at this now, so plot.imshow should be a similar, actually same image. What's happened there? So let's take a quick look. We've still got our images .as numpy. So this is now returning in, hold on, let's take a look at our error there, plot.imshow. Okay, clipping images, matplotlib, accesses. Do we need to get the first sample? Let's just take a look at our shape. Oh, it should be fine. Weird. Plot.imshow. Matplotlib, clipping, and we're not actually rendering anything. Zero. .shape. Weird. Let's divide it by 255. We should be able to render. Okay, so dividing it, it's probably because we've actually gone and converted it into float values, but that's fine. Okay, that's fine. Hold on for now. So just know that we've now gone and converted it into 250 pixels by 250 pixels. And we can validate that by typing in .shape. So you can see we've got 250 by 250 by 3, perfectly fine. What we're then going to go on ahead and do is this next step, which is exactly what I just demonstrated to get over that error. So we're going to take our images and we're going to normalize them. So or scale them. So we're going to take the results of this part of our pipeline and we're going to divide it by 255. So again, train underscore images.map, lambda x, and then x is going to be divided by 255. So we're going to go over every single value in our image and we're going to divide it by 255. So rather than our images now being represented as values between 0 and 255, it'll be 0 and 1. So again, deep neural networks like small values, just helps them generalize a lot faster. So if we go and paste that now and go and take a look at our shape shouldn't have changed. But if we go and take a look at our values, we've now got our floats, or well, values between 0 and 1. So if we now go and plot this out, plot.imshow, boom, we've got our images. So it looks almost identical. It's just the fact that we've gone and scaled our values. And you can see that it is now 250 by 250. So you can see that's 200. So that's 250 there. Cool. All right. So that is looking good. So that's our data pipeline. So we've effectively just gone and written that again so we can delete this. So that's establishing it for our train data, because remember, we're passing through the directory that we want to load up. We then need to do it for our test data. So that's doing it for our test images, and our test images are going to be stored in a variable called test images. Then we're going to do it for our val images because we are going and passing through our val images there. So again, we've now gone and loaded up our data. So we can go and access those by just typing in, preemptively hit that one. So either one of these. So we could go and type in val underscore images dot as numpy iterator dot next, and that's going to return our images. And if we want to plot it, plot.imshow, boom. Always good practice. And you can see that this one's being flipped over. This is actually being passed through the data augmentation pipeline. So when I was augmenting, one of the augmentation steps that I had was, horizontal or augmentations vertical flip. So this actually flips the image up and down randomly to give us a little bit more variability in our data. Cool. And again, we go through that in more detail in, you guessed it, the face detection tutorial. Okay, so what are we up to now? So we've now gone and loaded our images. The next thing that we want to do is load in our labels. And again, we're going to run through almost an identical pipeline to what we did here, but now we're doing it for our labels. So we're typing in def load underscore labels, and we're going to be passing through our label path, which is effectively going to be exactly the same or same style as what we're getting when we're listing our files up here. We're just going to get a path to our JSON labels. We're then going to be opening it up. So with open, and then we're grabbing our label path and we're extracting the value using .numpy. We're reading it and we're just double checking our encoding is set to UTF-8. This just helps avoid any unique or special characters. Then we're going to be having or being able to play with our value as, or play with our file as the variable f, and we're passing that through to json.load. So label equals json.load f. So this thing over here is effectively saying, hey, grab this file, and then I want you to hold it temporarily as this particular variable. So what we're saying is grab this file here, so label path.numpy, grab that file, which is going to be a JSON annotation. So if we go into, say we go into our train folder, labels. So what we might be saying is, hey, go into this org data train folder labels, and then grab this particular annotation here. So grab this thing, which currently has my class annotations. Remember, we took a look at that, and all of our key points. And I want you to hold that in memory temporarily as the variable f. And then what I'm going to do is I'm going to take that f variable and pass it to the JSON load function or method. And then I'm going to get my labels back. Then what I'm going to do is I'm just going to extract this key points value, which is this over here. And that's what I'm going to return back as part of my data pipeline, because I don't really need anything else. So if we actually go and run this, boom, then we've got pretty similar to what we had up here. We're going and using the list files function and then the map function. So this time we're going to be grabbing our annotations though. So train underscore labels equals tf.data.dataset.listfiles, exactly what we had up here. But now we're getting our annotations. So our annotations are going to be inside of org underscore data, train, and then labels. So we're going to do this for our train test and then val pretty soon. But this time our wildcard search is looking for any .json objects. So previously we were looking for .jpeg to get our images. Our annotations are in the JSON format, so we're looking for .json. And we are going to, again, set shuffle equal to false. And then again, we're going to be using the map function to be able to load in our data. So we're going to use a lambda function. We're going to pass through our label paths to our load label functions. So this little tf.py function bit is something that you've got to do if you want to use all of the base functionality inside of Python for specific functions. Now, in order to get the string out of the label annotation, this was something that I had to do. Again, took a ton of research to work out that that's what I needed to do, but we got it working in the end. So tf.py function is going to take in our load labels function. And then the next value that you pass through to that particular method is the input that you're going to be passing through to the load label. So rather than typing in load underscore labels x, we're actually saying, hey, use tf.py function. And then we're going to be using the load label. Again, it's a little bit weird. You're going to be using this load labels method or function over here, and we're going to be passing through the x value. And then we are going to be, or we need to tell it what it's going to return. So we're going to be returning tf.float 16. So that is effectively what I've gone and written there. So again, it looks a little bit weird, but that's what you got to do in order to use the data pipelines. And we're going to be returning that as train underscore labels over here. So let's break this down. So if we go and run this first line over here and go train labels. Nope, we don't want train images. We'll come back to that in a sec. Just train labels dot as numpy iterator dot next. This is going to return our just the path to the label. So org data train labels, and then this is the name of the file .json. And again, we could keep running next, and this would generate new options. Let me actually show. If I typed in iterator and then iterator.next. So that's one file path. So watch this file name over here. So this will change as we go through each individual one. So again, it's changed to 1. You can see, let me zoom in on this because that's probably tiny. All right, so that's the first one. My head covering that. Oh, that looks okay. Got to work out how to get that font bigger. All right, boom. So that's 10 now. Next one, 100, 101, 102, 103, 104, so on and so forth. So you can see we're just iterating through. That's how these data pipelines work. Okay, then if we go and apply the second step to our data pipeline to add that, and if we go and run this again, you can see we are now grabbing the actual annotation, so the actual coordinates. So we've now actually got the coordinates of each one of those annotations. Let me just double check what we're actually getting out of here. So the first value, 450 by 450, I believe so 640, all right, so it's going to be X for so the first value is going to be X for our left eye. Let's write this down. So these annotations, so the first two values to our X, I'm just writing, I can't even remember what I wrote. So X for our left eye, but it's good that you guys know. X for left eye, Y for left eye. And then the second two is going to be X for our right eye and Y for our right eye. Always super useful to really understand what is happening with your data. And I don't want to leave you in the lurch and go, hey, this is just your data, use it. All right, so if you take a look at how I've gone and actually written this data pipeline here, and again, if somebody wants to clean this up, by all means, go for it. I wrote this in a huge rush. I'm actually going away for work pretty soon, so wanted to get something out for you guys. All right, so left eye is going to be our first coordinate. So you can see that coords 0 and coords 1 represent our left eye. And I know that our first coordinate is going to be the X coordinate because we're dividing it by 640, which is the width of the image. So take my word for it. In this particular case, our first two coordinates are going to be X for our left eye, Y for our left eye. Second two are going to be X for our right eye, Y for our right eye. Okay, cool. So that is our set of labels now loaded. So again, we can delete that because it's just a duplicate. I'm going to leave this here because it's probably going to help you. We don't want it as markdown. Okay, so that's done for our train labels. Then again, we can repeat the steps for our test labels. The only thing that we're changing is the folder that we're looking in. And again, we can do it for our val labels. So we've now got all of our labels loaded. So if we go all labels in a data pipeline. So if we type in val labels.asnumpyiterator.next, boom, we got our coordinates. Remember, that's going to be X1, Y1, X2, Y2, and this is going to be for our left eye. This is going to be for our right eye. Okay, that's looking good. So that is our labels now prepared and loaded or set up as our data pipeline. Now what we need to do is bring them together. So if you think about how a supervised machine learning problem works, you're going to have your sample or your input and your annotation or your target, right? Now our input is going to be the image, the output is going to be the annotation. So in order to pass this through to our deep learning model, we need to combine them so that they are mapped together. To do this, we can use the zip method inside of the tf.data.dataset API. So this is what the dataset APIs actually is. So if we actually go, and if you're ever wondering, Nick, like, I don't know what the hell Nick is saying, so I just want some documentation. If you go to tf.data.dataset documentation, there's a ton of documentation on this, guys. So again, you can see it helps you build TensorFlow input pipelines. And there's a ton of examples. There's a ton of methods. So let's take a look at some of the ones that we've used. So we've used, we're going to use batch in a second. We've used map, because remember, we use map to map our file paths to the actual functions that load in our data. So we've used map. What else have we used? We've used list files, which actually looks inside. So that does that wildcard search for us. And I think that's all we've used so far, map and list files. We're going to use shuffle, batch, and prefetch in a sec. Okay, and we're also going to use zip. So the first line over here is actually going to concatenate our two data sets together. So again, let's grab this, do it step by step. So we're going to grab train or create a new variable called train. So this is going to be the final variable that we use to actually train our data. So train equals tf.data.dataset.zip. And what we're doing is we're combining those samples together. So exactly what I described. So we're going to map a input image and an output set of annotations. So by using zip, that's effectively what we're doing. It's almost like if you imagine a zipper like you've got on your jeans, we're effectively zipping them together so that one will map to the other one, right? Cool. Alrighty. So we've got train underscore images, train underscore labels. And now when we go train.asnumpyiterator, so it's similar to what we did over there, we're not going to get just an image or just a label back. We're going to get an image and its corresponding set of annotations. So if we go and run that, Might take a little while because there's a ton of data. And if we type in train.asnumpyiterator.next, boom. Now, if we take a look at the shape, might return an error because there's no shape variable, but that's fine. Let's take a look. Nope. So that's fine. So let's type in len. So you can see we're now getting back two different types of objects. So the first object, so if we go and grab object 0, that is our image. So we can type plot.imshow. Presto, that's our image. Now if we go and grab the second value, which is going to be index 1, this is our set of coordinates. So you can see that we've now got an image and it's mapping to a set of coordinates for left eye and right eye. And remember, x1, y1, x2, y2. Then what we're going to do is run it through my Mxshabbat pipeline, which is shuffle, batch, and prefetch. So shuffle effectively just shuffles your data. So if we go and do that, again, you're not going to see any change in output. Again, looks identical to what we had previously. The only change now is that it's going to shuffle our data as we read it in. So this just helps your model perform a little bit better. So if we go and run this a bunch of times, we're going to get different results each and every time because it's now shuffled. We're then going to batch it up. So rather than returning a single sample each time, we're going to return 16. And this is good practice to batch up your data and rather than just using one batch at a time, because that's effectively stochastic gradient descent. That's fine. So we're going to use a batch size of 16. If you start running into issues where your GPU doesn't have enough memory or it's slowing down way too much, try decreasing this number across all of the samples. So maybe you might try 8 or you might try 4. The higher in this particular case, I've found the higher the value this particular number is, or the higher the batch size, the more stable your training is going to be. But that's perfectly fine. If you got to go lower, it's okay. It's still going to work. Okay, so we are now going to batch it. And the core change once we go and batch is that if we now type in, so let's grab our images and let's grab so right now we've already gone and changed it. So let's actually go and type in .shape. Rather than returning a single image now, we're going to return 16 at a time. Let's take a look and you can see that there. So rather than returning a single image as we were previously, we're now returning 16 images by 250 pixels by 250 pixels by 3 values. Okay, and then we're going to prefetch. You're not going to see any change when we go and add the prefetch step. It just means that it's going to start loading images into memory as it's still training the other set. So this helps ensure that you don't hit any bottlenecks as you need to go and reload images. Okay, that is our data pipeline now built. Now we can go and delete this because it's exactly the same steps that we've got down there. So we went and batched, we went and prefetched as well. So if we go and run that is our training data partition now created, and we're going to do the exact same now for our test images and test labels, and it's going to be stored in a variable called test, and we're going to do the same for our val images. So val images, val labels, going to be stored in a variable called val. Another important thing to note, ensure that your shuffle size or the value here is bigger than the size of the number of images that you got. So I think I actually had more this should probably be closer to like 8,000. How many, we've already gone and batched it now. What's the length of our test images? 1,800, we should definitely bump this up. Let's make this 2,000. So this is the shuffle buffer size. And then let's double check our val images. That's this should be 2.2. All right, cool. I'm just giving it a little bit of room to breathe. And let's rerun that. Okay, cool. So those are our data pipelines now done. So we're now ready to get this data and pass it through into our deep neural network. So this is those steps are really, really important. Although they're a little bit tedious, really, really important. And now what we can do is actually view some samples. So we've now gone and let's go and take a look. So we've gone and loaded our images. We've gone and prepared our labels and loaded those. We've then gone and combined them. So remember the zipper, we've gone and zipped them together. And then what we're going to go ahead and do is view some samples. So let's open this up. So the first thing that we're going to go ahead and do is get our iterator. So we'll just we could actually name this whatever we wanted to, right? So this could be data iterator. In this case, we're going to call it data_samples. And we're going to set it equal to train.asNumPy_iterator. So exactly the same as what you saw me do up here. So if we go and run that is going to get an iterator. Now, the next thing that we're going to do is run data_samples.next. So this is going to get one batch of data, which we can then use to visualize our coordinates and our images. So if we go and run that, this is now going to get one batch of data. So if we type in res, You can see that we've got our images. So if we go and take a look at the length, it should be 2. So our images and our annotations. If we go and grab our images, so images are going to be index 0. And if we type in dot shape, you can see we've got 16 images of 250 pixels of 250 pixels by 3 channels because they're color. Okay, what's next? So let's actually go and visualize them. So in order to visualize them, there's 2 parts to this. First, we're creating subplots, and this is going to allow us to visualize multiple images at the same time. I've just created 4 different columns. So you could actually type in n rows and do like 4 by 4, but we're just doing 4 columns of 4 images. So the first line is figure, comma, ax equals plot.subplots, and we're setting n cols equals to 4. So this tells matplotlib that we want 4 different columns to visualize our images. Then the second keyword parameter is fig size. So this tells matplotlib how big of a plot we want. So you want it to be a little bit bigger to actually see these images, but I'll show you how to tweak that if you wanted to. Then what we're doing is we're looping through 4 different images. So 4 index in range 4, because we only want to visualize 4 images. We're then going and extracting a set of sample images. So sample underscore images equals res 0. So this is going to access our key, which brings back our images. So it's effectively doing res 0, right? And then grabbing 1 image. So let's say we grab the first image, which is index 0. We could actually go and plot this out. So plot.imshow. All right, that's our first image. Then what we're doing is we're getting the corresponding coordinates for that particular image. So we're going res 1. So res 1, because that's where our coordinates are stored. We're then grabbing the first set of coordinates, which in this case, so we're then accessing, so it looks like it's encapsulated in another set of arrays. We're then grabbing the first set of coordinates, which is going to be this. Now, you're probably wondering, Nick, why are they all 0? And that's because my eyes are closed. So you probably can't see my irises, hence why all of the annotations is 0. So this is what these 2 lines are doing here. Then we're using the OpenCV2 or the OpenCV method to actually draw the circles. So the full line is CV2 equals circle, and then we pass through the image that we want to plot onto, right? Or plot or draw the actual circles onto. So CV2.circle, and then we pass through the image. And then we have to do a little bit of transformations to manipulate our coordinates. So we are grabbing our sample coordinates. So we're grabbing the first 2, and remember the first 2 are going to be for our left eye, so X and Y. So sample underscore coords, and we're grabbing the first 2 using slicing. And then what we're going to do is we're going to multiply it. So np.multiply, and we're multiplying it by 250 pixels by 250 pixels. Any guesses why? I'll give you 2 seconds. 1, 2. Okay, so remember we went and scaled our coordinates to be divided by the width and height of an image. In order to go and render that back onto the image, we need to scale it back out. So in this particular case, our image size is 250 pixels by 250 pixels. So we go and multiply it by that, which is exactly that there. Now, OpenCV likes the coordinates being passed through as a set of integers. When we go and multiply a value, which is like it's a long float. So let's actually go and grab another sample. So if we go and grab sample 1, right. So if we went and multiply 0.3203 by 250, it is, wow, that's running a little bit slow. It's going to return 80.0749, right? Which OpenCV doesn't like. So instead of returning that value, what we're actually doing is we're encapsulating that. So let's just type in np.array. Right, so that's still the exact same value. So that's, imagine that's 1 coordinate, right? But what we can do is type in as type, and then pass through the type that we want to actually convert it to. So now it converts it. So now it actually converts it to an integer. Rather than having a float value, we've now converted it. So imagine we're doing that exactly the same over here. So we're grabbing this set of coordinates, we're typing np.multiply. Multiply. Wow, my typing's a shocker. And we're saying we want to multiply by 250 by 250 by 250 by 250. Boom. So you can see we've got all of our float values. Then we can type in as numpy or as type, sorry, and then int. Boom. So you can see we've now gone and converted it into a set of values that OpenCV is going to like. Now, remember that we only need the first set of coordinates to be able to draw 1 circle. So we're grabbing the first 2. What have we done there? We only need, so if we're going to grab the first two, we don't need to multiply by 4 values. So that's our first two. And then the other thing that OpenCV wants this as is a tuple. So we just wrap it inside of a tuple. Boom. So those sets of coordinates now actually allow us to draw a circle. So that is exactly what all of this stuff is doing there. Then we've got the size of the circle that we want to draw. So in this particular case, it's going to have a radius of size 2. The color, so we've set it to 255. So this will be a blue coordinate. And so it's just BGR. And then whether or not, or the radius or the line width. So -1 actually fills in the circle. So that is what this line over here is doing. Then we're doing exactly the same for the other set of coordinates. So the only change is we're now grabbing the last two coordinates, which will be for our right eye. And then we're actually plotting it. So we're actually using the axis figure. So the axis value over here actually returns each one of those different subplots. So we're grabbing axis 0. So because remember, we're going to be looping through 4 images and we're just using IMShow. So again, it's pretty similar to what you saw me do over here. So plot.imshow. Here rather, we're just going and saying, get me the specific plot section or plot column, and then use IMShow for that plot column. And this is what allows us to plot 4 different images at a time. And then to that, we're actually passing through the image that we've now gone and drawn the circles on, which is sample image. So if we go and run this, booyah, take a look at that. So that is our sets of images as well as our annotations now drawn. So you can see that there. So those little, it's probably a bit small. Let's actually just get rid of this temporarily. So let's actually go and make our circles bigger because I think right now they're a little bit small. So we can actually go and do that by bumping up this figure here. So let's change this to 5. Grab a next set of data. Boom, our circles are way bigger now. So you can see that way more clearly. So in this particular case, I would have thought that was BGR or is it RGB? Anyway, you're able to pass through the colors. So in this particular case, let's go and change this one. So let's go and set it to 0. So we know that this is our left eye coordinate. So if we go and change that, so you can see the color of one should have effectively changed now. Give it a sec. Okay, so that means our left eye is being shaded in as blue and our right eye is currently shaded in as green. So we can go and change that back. Let's make a note. So what is it? The red circle is left. Blue, what is it? No, green circle is our right. Okay, so that is looking good. Let's just change that back so we can go and rerun that. Oh, it's pink now because we've gone and applied it multiple times. There you go. Well, what have we gone and done there? Oh, it's because we haven't gone and zeroed out that value. There we go. All right, so we've got green and red samples. And again, looks like some of my annotations aren't all that great. So you can see that there. Now, that may impact how well our model is able to perform. So I think one of the biggest things that I noticed as I'm training this, and you'll see this towards the end, is that we could improve this by improving our annotations, just improving our data overall. But these look pretty good for now. Cool. So what have we gone and done? So we've gone and loaded in our images. We've gone and prepared our labels. We've gone and combined them. And we've gone and taken a look at how to view some of our samples. So effectively our images and our annotations. Let's jump back on over to our client and see what's next.
Now it's time to get rolling in the deep. All right, Adele, it sure is. Time to build our deep neural network. For this, we'll use Keras to design the net. How will it work? Well, we'll take an image as the input and output 4 values, 2 pairs of x and y coordinates, 1 for each eye. We'll use mean squared error as the loss function to hopefully generalize towards an accurate eye estimation. Cool, let's do it.
Okay, so it's time to get deep learning. So far what we've gone and done is we've gone and set up our environment over up here. We've gone and loaded in our data. So we're now good to go. So we can effectively take our train and our val partitions and pass it to our training run, or once we've got our neural network set up, and start to train this model. But before we do that, we actually need to create our neural network. So first things first, let's go on ahead and import some dependencies. So we're going to be using the sequential API for this. So again, 1 input, 1 output, or 1 input and then a 1 set of outputs. That makes it pretty easy to use the sequential API. So from tensorflow.keras, let me know if you want like an explainer on the differences between the sequential and the functional, because I think that one is really, really powerful. One is really, really functional. One is really, really, really easy to use. but there are differences in how to use them. So from tensorflow.keras.models import sequential. And then the second line, and you know what's funny actually, so I know I'm digressing, but I actually built this using the functional API and then rebuilt the entire thing and was like, hold on, we can simplify this a ton. So why not make it simple rather than going super complicated without the need for it? So hence why I have now gone and rebuilt it with the sequential, or this tutorial with the sequential API. So from tensorflow.keras.models import sequential, and that is going to give us our sequential wrapper for our neural network. Then I've gone and written from tensorflow.keras.layers import input, conv2d, reshape, and dropout. Okay, so input actually is going to be used to define the shape of our input. So in this particular case, it's going to be 250 by 250 by 3, because we've got a picture which is 250 pixels wide by 250 pixels high by 3 channels deep, because it's color. Conv2d is going to be used to actually do our convolution. So this is going to give us information about the image effectively. It's just a really popular neural network layer. And again, if you want an explainer on that, hit me up. Reshape, you'll see this in a sec, but we effectively use it to condense our outputs from our neural network. Dropout applies a bit of regularization. So what I was noticing when I was originally building up this neural network is that we were getting really good performance on our training partition, but testing was sucking, or our validation partition was sucking. So one way that you can fix that is to use dropout, which is a regularization technique. You can also look at applying L1 and L2 penalties. Okay, so that is that. Then the big boy. So this over here, so from tensorflow.keras.applications import ResNet 152v2. So this gives us our backbone architecture. So I talked a little bit about this in the breakdown board. This is effectively standing on the shoulders of giants. So we're taking a pre-existing neural network and we're customizing it to give us exactly what we need. This is common practice out there in the industry. You'll see in a lot of big and state-of-the-art neural networks, people will use pre-trained computer vision architectures and they'll just fine-tune or add the additional layers that they need to get the outputs that they want. Exactly what I've gone and done for you guys. So if we run that, that is our models, layers, and backbone architecture now imported. Let's go and take a look at our neural network. So, and I'm going to do a little bit more of a deep dive into this for you, because I think it really helps when you see how these are designed or how I design them. And it might not be best practice, guys. I'm not perfect, but I want to show you nonetheless. So let's say, for example, you needed to work out how to actually build this. The first thing that we know is that our input shape has to be 250 pixels by 250 pixels by 3. So we can actually define an input. So if I go and grab this, so I can type in input equals that. I shouldn't have typed, let's call it input layer. Right, so input layer equals that. Now we can actually take a look at our input layer. And you can see right now, it says that our shape is 250 pixels by 250 pixels by 3. So this is actually how I do it in actuality, guys. So I'll actually just look at each one of these layers step by step as I'm building them up. Okay, so I know that I've got my first layer, right? And I know that my input layer needs to be 250 pixels by 250 pixels by 3, because that's the first layer that's going to be hit, right? Then let's say I wanted to go and add in this backbone architecture, yeah? Well, then what I would actually do is I'd go and say, let's go and create it and call it backbone equals ResNet 152v2. And then by default, ResNet is a complete neural network. So it's a pre-trained image classifier. Now, we don't want the final couple of layers from that particular neural network. And you can verify this, right? So if I type in question mark, after that particular layer, you can see that it's got this ability to drop the top bit. So if we go and take a look at include top, it says whether or not to include the fully connected layer at the top of the network. We don't need that because that fully connected bit is actually the image classifier bit, and we don't need that. So what we can actually do is pass through include underscore top equals false, right? So that's our second layer. Now, in order for these to be connected, because that's a big part of neural networks, we need to pass in the input to this backbone layer that we've just gone and created here. So we can actually create another set of parentheses and pass through our input layer. Boom. Cool. So this neural network layer, the backbone architecture is pretty big. Just bear that in mind. So it might take a little while to download if you're running it for the first time. Okay, so if we now go and take a look at our backbone, you can see that our shape is 8 by 2048. And I think if we type in .output, can we get our output shape? Might not give it to us. Doesn't look like it wants it. So we can typically, how do I normally do this? I'm trying to think of what's the best. So it gives us I think that actually is the output shape. Right, let's actually run this for a second. Yeah, that is the output shape that is being returned there. So over here, we can see that is going to be our output shape. So it's 8 by 8 by 2048. I just wanted to double check that I'm telling you the right thing, because nothing worse than somebody goes, yes, this is this, and then it's not. And you're like, what is this guy talking about? All right, cool. So we now know that the output of this particular neural network is going to be the batch size, which is what this none represents, by 8 pixels by 8 pixels by 2048. So it's gone from a really big image to a condensed image, but a much deeper one. So that's what our backbone neural network is giving us. Now we know that we need to somehow take these sets of values from 8, 8, and 2048 and reduce it all the way down to a set of 4 values, which is going to represent our 4 different coordinates. So somehow at the end of the line, we're going to add in all of our hidden layers here. And then effectively our output layer is going to equal, it needs to equal 4. That is what our output needs to be. So if I go and now add in this conv layer, right? So let's add this. So let's call it CNN1 equals this. And again, we're going to we need to connect them up. So we're going to take our backbone and we're going to pass it through to our conv2D layer. So I can now type in backbone. Let's get rid of this, these two. Let's just add a comment here, right? So if I go and run that now and take a look, so CNN1, let's take a look. So now our output is 8 by 8 by 512. Okay, so we've now gone and condensed the output or the final channel. So we've now effectively gone and reduced that data a little bit. So we might want to add a little bit more of intelligence to our neural network. So let's say, for example, we wanted to go and add in another convolutional layer. We could do that. So we might type in CNN2, and I'm just explaining how I actually build these because sometimes it's a little bit black magic, right? So we can now type in CNN1 or pass through CNN1 to that CNN2 layer. So if we go and take a look at CNN2, this will give us the exact same output, just to keep keeping it in mind. So again, we've now gone and added another convolutional neural network layer, which is going to output 8 by 8 by 512, which is exactly the same as what our neural network is telling, or our summary is telling us down here. And I'll explain that a little bit more. Then we can add in, let's say we wanted to start condensing this final channels layer now. So we've gone and effectively condensed it down from 250 by 250 by 3, but we've still got a ton of channels. We can now reduce the number of filters that we've actually got in our convolutional neural network by changing that first parameter, which is effectively the number of units. So if we go and add that now, CNN3, lowercase, CNN, nope, lowercase. So we're going to pass that convolutional neural network layer, and we're going to pass through CNN2. And this is literally how I design these for you guys. So, or when I'm doing it in practice as well. Right, so we've now gone and condensed it down. So remember that previous output was 8 by 8 by 2, 8 by 8 by 512. We're now down to 4 by 4 by 256. And the reason we've actually reduced these first two values over here as well, so the spatial component, is because we've gone and increased the stride of our convolutional neural network. So these three parameters, so 256, 3, and 2 are really important. So 256 defines how many filters we're actually going to have in our convolutional neural network. The 3, or the second parameter, defines how big each one of those filters are going to be. So in this case, we're saying 3 pixels by 3 pixels. And the 2 is actually referring to the strides component of our convolutional layer. And that defines how fast these filters actually move across our image. So 2 basically means it's going to move 2 pixels at a time. So rather than moving 1, 1, 1, 1, we're actually now going to go 2, 2, 2. So this means we're effectively condensing down the amount of data we're getting back again. Padding same effectively doesn't, let's actually remove it, right? So if I remove padding, right? So if we take a look at the moment, our output is 4 by 4 by 256. If I remove the padding, which effectively pads out the outsides of the images so that we can run the filters across the entire set without cutting or concatenating stuff. Not concatenating, what is it? Chopping off. I can't remember the fancy word for cutting stuff off. So if we go and delete that, let's go and take a look. So what removing the padding does. So remember pre-padding or pre-removing padding, our output was 4 by 4 by 256. Now it's 3 by 3 by 256. So again, you can tweak this. So as long as the end output that you get to is that 4 value, and again, there's going to be best practices for specific neural networks, but this gives you an idea. So if I go and add padding back, and I'm going to set it equal to same. So the 2 values that I think you can pass through to here are same and valid. So by default, I think it's valid. Let's double check that. Yeah, by default, the padding is valid, which means that it's only going to convolve across the sections of the image that have valid data. Or effectively, if it gets to the edge of the image, it's not going to be able to apply the filter, right? So if it gets to the edge of the image and there's 2 pixels outside of it, it's not going to work. Hence why it says we can either pad it out or we can just not convolve over that particular region. Okay, what have we done? We've gone and added, 1, 2, 3. So we're now up to CNN3. And again, this is all I'm doing here. So I'm now going and adding another convolutional neural network layer, and this one doesn't have padding, so CNN4. And now we're going to, again, hook it up. So we're going to type in CNN3 is going to be passed through to our new layer. So CNN4 now, let's check our output. So the output is now 2 by 2 by 256. So you can see we're getting closer towards that 4 values. Now we're obviously going to need to do something pretty drastic to get back down to 4, but that's perfectly fine. Well, you can see that we've now gone and got close. Now the dropout bit is effectively a layer that I've gone and added in order to improve to ensure that we don't overfit. So it's a method of regularization. So again, you can add these at different stages within your neural network. And you can change how much or how many parameters you actually drop out. So let's say, for example, we want to drop out 50% of the previous layer at any given time. We can go and set this to 0.5, but that's pretty strong regularization and it might throw stuff off. Hence why I've set it to 5%. I found 20% didn't really work. 10% didn't really work, and even adding 2 dropout layers. So if I wanted to, I could actually add 2 dropout layers or add another one here if I wanted to. But we'll come back to that. Okay, so let's get down to our 4 values. So now we're going to add another convolutional neural network. So now we're going to call this CNN5. And we're going to pass through CNN4. Now if we go and print out CNN5, we should be getting close. Oh, we're close now. So we've now got values 1 and 1 and 4. So this means we're going to be outputting a set of 4 values, but they're going to be inside 2 sets of arrays. Now, it'll work at this stage, but we'll need to do some tweaking if we want our loss to work correctly. Hence why I've added this reshape bit. So because 4 multiplied by 1 is just going to be 4, we can actually reshape it and say, hey, just give me back 4 values for each sample. So let's grab this and let's add our reshape layer. So we call it reshape. And again, we're going to hook it up. So we need to pass through CNN5 to reshape. CNN5, boom. There you go. We've now got a set of 4 values, and that is our neural network now defined. So think about how we did this, right? So we started off with 250 pixels by 250 pixels by 3 channels. And by adding all of these layers or all of these hidden layers, we've now effectively mapped it down to our set of outputs, which represent our 4 different values. Now, there is going to be best practice depending on what type of model you're building, but I wanted to give you a feel for how I actually design these and get them working. So that is effectively what I was doing. And I tried a bunch of combinations, tried a ton of stuff that some of it didn't work. Some of it definitely did work a lot better than others. But that is our neural network now built. Now, rather than defining it this way, because this isn't actually encapsulated inside of the sequential API, so we can actually delete this. We don't need that anymore. So what we can do is we can actually define a new sequential class, so model equals sequential. And you can see I've got a set of parentheses and then inside of square brackets. So we're passing through an array of all of the different layers in their correct order. So exactly what we were designing up there. So we had our input, we've got our ResNet, we've got our convolution or our 3 convolutions. We've then got our dropout layer, which is our regularization layer. We've then got another set of convolutions. And remember, at that stage, the output was 1 by 4. Then we go and apply a reshape layer to give us just those 4 values. So if we go and run this now, that is our neural network now defined, and it's all hooked up. You don't need to pass one layer into the other. It just works. What's happened there? We'll probably run out. We're probably going to change our padding. All right, this is good that you're seeing this. So what have we gone and done? So Okay, so this is saying an exception has occurred when calling layer reshape 2. Total size of new array must be unchanged. So we're trying to go from 2 to 2 to 4, and it's saying the output is 4. So we've clearly gone and changed padding at some stage. So what have we gone and done? Let's go and check what we had originally. Have we gone? I think we went and deleted a layer. So 3, 3, 3. Do we delete a layer here? So 512, 512, 256. I think we need to add one back. Yeah, because we had this one over here. I think we cut one out. My bad. So let's go and add that one back. Okay, let's actually dive into that error before I just go and fix it. So this is basically saying that we're trying to reshape an array of size 2 by 2 by 4 into the value of 4. But that means that we've got 2 values by 2 values by 4. Not going to work, right? So there's 16 values that we're trying to reshape into 4 values. What this is effectively saying is that we can't take that output of the previous layer and reshape it into what you're asking, Nick. So we need you to do a little bit of additional transformation, perhaps add in some new layers to be able to do that. So we can add in another convolutional neural network layer. I think let's double check that. Okay, that's still compiling. Okay, that looks okay. Yeah, let's just check. So I must have deleted a layer previously. So let's disable scrolling. So previously before we went and run summary or went and ran the summary, we had 512, 512, 256, 256. We've now got 512, 512, 256, 256. But there were 200. Oh, that's the dropout layer. That's fine. Okay, cool. Boom. That looks fine. Let's go and run our model summary again. Beautiful. Again, 70. Oh, all right. So let's come back to that. So we've now gone and defined our model inside of a sequential neural network class. We can then run model.summary. This is your lifesaver. So whenever something isn't working, normally what I'll do is I'll take off layer by layer. So I'll strip it back. I'll go, all right, what's the output of the first layer? What's the output of the second layer? What's the output of the third layer? And I'll break it down just to ensure that I'm passing through the correct outputs into the next layer. And that is what we've got here. So we've now got all of our different layers. So we've got our ResNet, which is our backbone neural network. We've got let's take a look. And this over here actually tells you what type of layer it is. So you can see this one's a conv2D. This one's it's probably a bit small. Conv2D, 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 dropout, conv2D, reshape, which is exactly what we had from over here. And this one's a functional one because it's one that we've downloaded from the applications. There's a ton more, right? So if you type in Keras applications, you can actually review all of the different pre-built neural networks that you can use as backbone layers. So you can see that there are a ton, right? So there's ExceptionNet, VGG16, which we use for the face detection model, DenseNet, EfficientNet, ton that you can use. And they actually evaluate what the models actually look like. Okay, so that is our neural network now built. So we can see all of our different layers. We can see the output shape. We can also see how many layers actually have, or what the total number of parameters is, what the total number of trainable parameters is, and what the total number of non-trainable parameters is. So this value here is the one that you need to pay attention to. The larger the neural network or the more number of trainable parameters, the longer it's going to take to train because there's more stuff that it needs to learn. So that is quite a large model. So 71 mil, obviously. All right, cool. That is our model now built. So that is step 3.1 now done. So we can go and delete that. Okay, we're looking good. So let me know if you thought that that was useful. So me actually stepping through building that neural network. I debated whether or not I'd talk to you about it, but I figured, hey, if it helps you understand what's happening, might be actually useful. Okay, so that is our neural network now done. The next thing that we need to do is we've really got two additional steps. So we need to compile our model. And by compiling, we need to actually go and pass through the optimizer and the loss function. So first things first, let's go and define our optimizer and our loss function. So our optimizer is going to be an Atom optimizer. Again, there's a ton of different ones that you can use if you want to use that. So we are creating a variable called optimizer and setting that equal to tf.keras.optimizers.atom. We're passing through a learning rate of 0.001. So again, if you wanted to slow the learning rate or speed up the learning rate, you definitely could. I found that a faster learning rate just went crazy. A slower one took way too long. This is a happy medium. And then we're setting how fast we actually want our learning rate to decay. So as we train, we want our learning rate to slow down so that we don't miss our global minima. We don't effectively miss the point at which our model is generalized. And that is what decaying does. This is common practice to slow down your learning rate the more that you've trained. And that is what that decay parameter actually dictates, how fast to decay. All right, so that is our optimizer stored inside of a variable called optimizer. Then we're setting up our loss. So loss equals tf.keras.losses.mean squared error, because we're going to define the difference between our predicted values and our true values in terms of our coordinates. So those are those two. Then we can compile. So we can type in model.compile, and then to that we pass through our optimizer and our loss function. That's our model good to train now. So we could actually make some predictions right now. They'd suck, but we could actually do it right now. And that's exactly what we're going to do. This is really good practice. So just double checking that the predictions that you're outputting make sense and that they are, so if you're expecting values between 0 and 1, are they outputting values between 0 and 1? If you're expecting values which are only positive, are they outputting only positive? So this is another step that I typically go through. I'll sense check my predictions. So again, we can grab some data. So we can type train.asnumpy iterator.next, and we can unpack those values. So X is going to represent our images, Y is going to represent our labels. And then what we can do is check the shape of our images. They should be 16 by 250 by 250 by 3, which they are. And then we can actually pass through our images to our model right now. And again, it's not trained, so the accuracy is going to suck or the performance is going to suck, but it will work. And it's good to check this. We can pass through our images to model.predict, and we are going to get back our scores, or effectively our coordinates. So this is coordinates. And those are our coordinates. So you can see that we've got all of our coordinates there. Now, some of them are negative. In theory, we shouldn't have negative values. So you could add a sigmoid activation to the bottom here. Now, I didn't add one because I found that it screwed around the training a bit, but you definitely could. Now, keep in mind, activations act as a modifier to our neural network. So if we type in, my computer's like slowing down randomly, sigmoid activation, it would take the output of this particular convolutional neural network layer as it stands, and it will pass it through a function that is represented as this. So it would take whatever output, be it positive, negative, and it would shape it to be between 0 and 1. So let's say our output from our neural network was -4. It would then shape it to be, what is that? So let's say 0.0001, for example. So this effectively acts like a modifier, and it helps our neural network learn non-linearities. Okay, so that is that now defined. So we've now gone and taken a look and made some coordinate predictions. And again, you can test this out before training. It's good practice to do that. So that's exactly what we've gone and done. Now, the next thing that we actually want to go on ahead and do is train our model. So we want to effectively train our model for what I found, or the model that I'm effectively going to show you in the end is a model that's been trained for about 100 epochs. It's pretty good. It's not perfect, but I wanted to show you the process anyway. So in the interest of time and actually getting this tutorial out in a reasonable amount of time, what I'm going to do is I'm going to set this to train for 5 epochs. On my GPU, it takes about 2 minutes to train each time, but what the final model that I actually trained was actually trained for 100 epochs. So just a key thing to keep in mind, but let's demo 5 epochs for now, and let's actually see what our performance looks like. So in order to do that, we are going to type in hist. So by saving or by passing through the model.fit function to a variable, we're actually able to store the history of our model, right? And this is in terms of our loss functions. The loss functions, remember, right up here, we defined it as mean squared error, and we passed it through when we went and ran model.compile. So that's that bit over there. So inside of history, we're actually going to get our validation loss and our training loss. So we'll actually be able to unpack those and see what our performance looks like. To actually run training, we can run model.fit, pass through our training data, specify how long we want to train for, so in this case 5 epochs, and then also pass through our validation data. So our validation data will pretty much run the exact same train step, it just won't go and update the weight. So it'll evaluate the performance. So it's just a forward pass through our neural network. So again, it's still going to calculate mean squared error. Okay, so hist equals model.fit. We're passing through our train data. We're setting epochs equals to 5, and we're setting validation data equal to val, which was our val partition, which we set up right at the start. Let's go and run this. We'll review performance. And then what I'm going to do is we're going to load up a model that I baked earlier and see what that actually looks like. So let's go and run this. And assume all things holding equal, it should kick off training. So it's probably going to slow down my computer at the moment because I'm recording as well. Let's actually see. Drink break. Snack break. I can hear my GPU spooling up as we speak. All things holding equal, this should start training. Sometimes it takes a while to start. If it holds for quite a while, then that might mean, okay, so that looks like we've probably run out of VRAM. Let me actually show you this, right? So if we actually go and scroll down. Okay, so this is saying hint if you want to see a list of blah, blah, blah. This is basically saying wherever you see OOM, this means that you've got an out of memory error. And sometimes this is caused by you having too large a batch size. And other times it's just because you've got other stuff running, which might be taking up your GPU as well. Two things that you can do to try to fix this. So first thing is go and reset your Jupyter notebook. So let's try that first. So if I actually go over to here, so we can actually go, let's open this up. You can see the computer slowing down massively. Might be time to invest in that 3090, guys. So what I'm going to do is I'm going to stop this kernel. So I can go to my Jupyter notebook that I'm running right now, right click it, hit shut down. And sometimes because I was actually defining that neural network outside just to show you those layers, that might take up VRAM as well. So then when we go and redefine a new neural network, it doesn't have enough space to run. And keep in mind the ResNet model is quite big, so it might take up quite a fair bit of space. So there's two things that we can do to try to fix this. So we can either reduce our batch size or try clearing our memory. So let's just double check our GPU RAM has been cleared. And it has, so you can see that we don't have any GPU in use at the moment. So let's go and redo our imports, reset our out of memory, reload our data. I know, painful, got to do it again. It's part of the fun. Reload our images, reload our labels, and then reload our training data or redo our combining of data. I'm not going to view our samples. We definitely could, but we don't need to this time. We've already done it. We're going to redefine our neural network. Bang, bang, bang. And then we're going to redefine our optimizer. Boom, boom. And let's kick off training. Do we need to run that? No, we don't need. So let's try running that now and see if we get that error again. If we get it again, then what we should effectively try to do is drop our batch size. But I'm recording at the moment, so I've got a feeling maybe it's taking up all the GPU. So if we go and take a look at our task manager, we can see that our GPU is scaling up. Looks like stuff is happening. All right, you can see that it's definitely picked up there. Now it's actually started training. All right, we're in business. Cool. So you can see that our model is started to train. So it tells you the status. So we've got 1 epoch out of 5. We have 480 batches of data that we're going to be training on. It's going to tell us how long it's going to train. So in this case, it's taking roughly 2 minutes to finish off this batch. So that means if we're going to run it for 5 epochs, it's going to take roughly 10 minutes overall. So that's just a good thing to note. Now, if you were going to do it for 100 epochs, that obviously means that it's going to take significantly longer. So 200 minutes. But in this case, that's going to go on training. So as soon as it actually finishes training for 1 epoch, it'll actually calculate the mean squared error for the validation partition as well. So let's let that finish training and then we'll be right back once it's all done. But for now, it looks like things are happening and our neural network is training. So we'll be able to check it out in a second. So again, I'll be back in 10 minutes. Peace.
A little longer than a few minutes later.
Alrighty, and that is our neural network now trained. So you can see that we've gone and run through all 5 epochs successfully. And if we take a look, so what's important when you are doing this is to ensure that your training loss and your validation loss are at least both heading in the right direction. They might not decrease at the same speed, but they are both heading in the right direction. So you can see that we started off with a mean squared error for our training partition loss of 0.703, and then it finally dropped down to 0.0016. Likewise, we started off from our validation partition of 0.0297 and ended up with 0.0197. So we've definitely both decreased. When I did this for 100 epochs, I got pretty close to both of them being below 0.0001. I think it was something around that. So just bear in mind if you're going to train this properly, train for the full 100 epochs and see what your model performance definitely looks like. And I'll actually show you what the final model does look like as well. But for now, let's jump back on over to our client and see what they think.
We're done, son. Time to review performance. All right, let's go do it. No questions. Wait, what are we doing again? We're going to take a look at how the model performed by analyzing the training and validation losses. This is to review whether or not the model is generalized and also to check it hasn't overfit. What about saving the model? Oh, we'll do that as well using the keras save function.
Okay, so what we now need to do is review some performance. So this is always good practice just to see how your model is actually performing. So if we go and review our loss plots, so remember, because we went and saved the model fit function to a variable called hist, that means we can actually access our model's training history. So if we type in hist.history, boom, you can see our loss and our validation loss. So that is that, and it's stored in a dictionary. So if I type in type, you can see both of them there inside of a dictionary. Now, what we can actually do is plot them. So remember right at the start when we were talking about matplotlib also has a plot function, which allows you to plot out different components of data. So what we're doing is exactly that. So plt.plot, and then we are passing through the hist.history loss component. So it's effectively hist.history loss. So we're sending that array of data to our first plotting function. So hist.history loss, and we're setting the color for that to teal. I don't know, just a fancy color. And the label for that is going to be loss. So that is effectively our training loss. Then we're setting our validation loss. We're pretty much the exact same line, but rather this time we're sending our validation loss data. So if I type in val loss, that is the array we're going to be passing through. So we're sending that, and the color is going to be orange, and the label is going to read val loss. We are then setting the title for our plot. So plot.subtitle, and we're setting that equal to loss. Again, loss quite a fair few times. We could call it loss plot. And then we'll, I don't know, training versus val. That's a bit better. And then define our legend. So plot.legend allows you to see which line is which, and then type in plot.show to actually show it. So if we go and run this, that is what our plots look like. Okay, so it looks like we're going okay at the moment, but we obviously haven't trained for long enough. I would never advise you to go just for 5 epochs and be happy with that. I would keep going until I'd see that particular loss or the loss start decreasing or stopping. So that is good practice. Keep going for as long as you can. I went up to 100 and it was still decreasing. So just the thing to bear in mind. But in this case, we are looking good. So our base loss is reduced and our validation loss has gone down as well, although you can't really see it because it's a very small, minute component. But this is still not going to be all that accurate because that's the mean squared error. That means on average, 0.0197 multiplied by to the power 2. That means on average, each one of our coordinates are going to be 0.3. I think that equates to distance. It's going to be that much off. So it's not all that accurate at the moment. But let's actually take a look at our performance to begin with anyway. So what we can do is actually make a prediction on our test set. So again, we're going to now get some data from our test partition. So we can run test.asNumPy iterator to set up that iterator, and we're going to save that as a variable called test_data. What we can then do is get the next batch, and to do that, we go to our iterator, which is called test data, which is what we just defined here, and we grab the next batch by running .next, and that is going to be stored inside of a variable called test_sample. So that's getting our test batch now. And then what we can do is pass it through to our, we should actually do something like, no, I don't want to screw this up because I screwed up the visualization last time and it caused a whole bunch of dramas. But our test sample is over here. So remember the test sample is going to be comprised of 2 components. It's going to have our X values, which are going to be our images. And this is going to have 16 images, remember? All right, 16 images. It's going to have our annotations, all of our annotations there. So lots of zeros showing up there. So it looks like we might have eyes closed or something, for example. We just want to pass through our images to our model.predict function. So model.predict, and then we pass through our images, which is the first index in our test sample variable. And we're going to store the values or the predictions inside of a variable called y-hat. So if we go and run that now, then what we can do is run our plot. So this is almost identical to what you saw when we were visualizing this. So I won't go through this in too much detail, but just know that we are using the exact same functionality to go and plot it out. So again, we're creating our subplots, which are going to have 4 columns. We're looping through 4 times. We're extracting the images and the coordinates. We're then using the circle method from OpenCV to actually visualize them. And then we're plotting them out using the index.show method. So again, let's take a look. All right, so looks like a lot of these images, we don't actually have our irises in the frame, hence why you can't see detections, and that's by design. So we've actually got some negative samples. This one is looking a little bit off, but remember we saw that weird annotation at the start, and I'm wondering whether or not I just got a little bit lazy, or whether or not the albumentations library has gone and thrown off some coordinates. But again, that'd be something that we follow up later on. So that's one sample. So again, we could keep running this. Let me zoom out a little bit. You can see it a bit better. So we could keep running this next cell, and this will give us more detections. That one's not looking too bad. So you can see that we've got the red is going, what do we say again? So red is left, and then the green is right. So that looks okay, right? Not great, but okay. So remember, green circle equals right. So that's okay. So again, we've got a large number that are outside of the frame, but again, we've only trained for five epochs. So we could go run this again. Looks like that one's okay. This one's completely off. All eyes closed. So lots of negative samples here. This one's looking pretty good. So I think when my face is directly in front of the frame, we're performing actually pretty well. Here it's looking weird. And this, I mean, I haven't done too much error analysis, but I've got a feeling that something might have gone weird with the annotations. But just bear in mind, error analysis and reviewing your annotations is really, really important. But I'm going to show you a finer tuned model in a sec as well. Okay, so that is looking good, and we've effectively gone and made some predictions. The last thing that we actually want to go on ahead and do is save down our model. So let me zoom in. So we are, in order to load our model, once we've saved it, we need to be able to use the load model function. So from tensorflow.keras.models import load model. So we'll load that in, or we'll import it. And then we are going to save this as, let's call it iTracker 5 epochs. So we're going to run model.save iTracker 5 epochs.h5. So we're going to pass through. This is effectively the file name for the file that you're going to save down. And this is just going to save in our root directory to begin with. So if we actually open it up here. So this big boy bat over here is the 100 epoch model. And I'll try to share it if I can so you guys can use it. But it's quite big, and GitHub's got a 100 meg limit. That's 280 over there. All right, but that's fine. Let's go and save this. So model.save iTracker 5 epochs. So you should see it pop up over here. And you can see that that is now saved. So we could go and reload that same model. So I could just grab that file name, pass it over here. That is our model now reloaded. And then we could go and again make a prediction and see what that looks like. So that looks okay. So again, we're getting predictions. And again, we could go and run this sample over here. Zoom out a little. Run this. So again, exact same model making similar predictions, right? Nothing crazy. So that is effectively this component now done. Now, before we wrap this up, I wanted to show you or to load up the better model. So let's actually copy this. And so this is called iTracker resnet.h5. So exact same model. The only difference between the 5 epoch model and this model is that I've gone and trained it for 100 epochs. So just significantly longer, right? Exact same data, no other changes. So I can go and load that model by just passing through that H5 model or that H5 file, and I'm going to get new predictions. So again, it should still work. So you can see we're going and generating predictions again. Now, if I go and make new predictions up here, this will be based on the 100 epoch model. So if I go and run that, so you can see way, way better. So take a look at that. So it's actively getting the correct eyes. This one looks like it's mixed them up a little bit, but it's looking a lot better, at least in... I don't actually know whether or not flipping was a good augmentation, because when are you going to be doing iris detection upside down? But that's fine. Let's keep taking a look. Let's make some new predictions. So again, that one's looking pretty good. So it's detecting... so what is that? The red will be my left, which is the opposite way. So yeah, that's good. So let's make some more detections. You can see that the 100 epoch model is significantly better. Not perfect, but again, way better. So over this, when we're straight in front of the camera, it looks like it's performing pretty good. Okay, that is our model now trained, and we've also gone and tested it out. Let's jump back on over to our client and then finish this up.
All right, home run, baby. Is it though? Yes, it is. We've got one last thing to do to test out our model, and as always, we like to put our machine learning to the test. Here we're going to try real-time detection to see how well it's actually working. What about potential improvements to the model? There are always improvements to be made. I think first things first, we could take a look at using a different loss function as well as providing better data after error analysis. This would help improve the model significantly. Given the fact that loss was still decreasing, we could also probably train the model for a little longer. Nice. Let's wrap it up.
So, as per usual, I like to finish these off with almost like a real time or a real situation type semi-deployment. And that's exactly what we're going to do. So the final thing that we're going to do is we're going to test out real-time detection. So inside of step 5, let's actually zoom in a little. So first thing that we're going to do is actually define the function that is going to do this. Now, this might look hardcore, but you've seen the majority of this code here before. So this is the exact same code that we use to actually go and draw our key points. So again, sample coords, and we're using the cv2.circle method to draw it. The only difference is that rather than actually grabbing data from our test sample or from our test partition, we're actually grabbing them in real time from a webcam. So in order to do that, we are using OpenCV, as you've seen me do a bunch of times before. First thing that we're doing is we're defining a video capture component, and this is going to break because I've got the wrong device number because I'm recording on video capture device 1, but we'll fix that in a sec. So cap equals cv2.videocapture0. We're then going to keep looping. So while our camera is open, we're going to loop and loop and loop and loop and loop and loop. Then in terms of what we do in that loop, we are first up going to read the frame from our camera. We're then going to resize it to be 450 by 450 pixels. So again, by default, it'll read in at 680 by 480. So we actually want to cut that, 640 by 480. We're going to cut that down to be a smaller frame just by doing some slicing. So frame equals frame, and then we're starting out from 50 pixels. So what is it? It's height. So it'll be, is that height? No, it's width. Yeah, it's width. So it'll be we'll grab it, start at 50 pixels and go to 450 pixels past that, which is the 500. Then in terms of height, we'll start at 50 pixels and we'll go 450 pixels down, which is the 500. Then we're grabbing all the channels. Then what we're doing is, because OpenCV reads images in as BGR, we need to convert it to RGB. So we've written RGB underscore image equals cv2.cvt color. We grab our cut down frame and pass it to that function. And we specify the color change code, which is cv2.color underscore BGR to RGB. And then the last thing that we do is we resize the image to be 250 by 250 pixels, which is just a scaled down version of our 450 by 450 image. Because remember, when we went and scaled down our image and passed it into our training partition, that's what we went and did. So there was less data to process. Then the last thing that we actually do is we divide it by 255 down here, and that is what gets passed to model.predict. And then if we actually go and run this, it's going to break now. But if we go and set the video capture device to maybe 1, let's run this, see if that works. So again, this is going to be running on a loop and making detections. Okay, so that looks okay. So take a look. So this is actually making detections right now. Now I've got a feeling that because I'm using a different camera and because I'm at a different angle, it's not as great as it was previously. Let me move over here. Let's drop the green screen. So that looks okay. What about the lights off? Not great, right? And this is, I think, because we're detecting at a different angle to what we actually went and trained on. But the other thing that I'm thinking that we could try is whether or not, if I opened up the blinds, whether or not we had more light, natural light coming in. Let's test that out. Okay, so it's still performing okay. Now, again, keep in mind it is a different camera. So it is tracking our eyes, doing well. But what I want to do is, rather than detecting with a new camera, which is slightly off center, let's maybe try to move this camera to be in a more similar situation to what I actually collected the images with. So if I bring this a little bit over here, bring it up there, how's that? So it's not too bad. I mean, it's definitely not perfect, but you can see that it is definitely at least tracking the eyes. So again, I think that in order to improve this, you'd definitely go for a bunch longer, about with lights on. It was detecting really well over here when I was testing it out. So for whatever reason, for some regions, performs a lot better than others. But again, we'd probably go and train for a lot longer. So what about if we close out? All right, so if we cover our face, that's performing okay. Bring it back. Still not perfect, but I think that's okay for a beginner. We can move back. It's a bit sketchy, isn't it? You definitely train. I'd be training for this for way longer, but that at least gives you an idea as to how to go about beginning to do it. Let's try changing the webcam. So let's see if I'm going to have to disable the webcam on the recording, but let's actually try switching it up and see what happens. Okay, so I've disabled the camera. I'm invisible. Now, if I go and change it to video capture device 0, let's see if we can pick this up. Okay, so you can see that that is definitely detect. I wonder if it's also whether or not we've gone and changed. You can see that that's picking up my eyes a little bit better. Again, camera sensors might change the impact of how this actually performs as well. You can see that that's tracking at least a lot better. Not perfect on the irises, but it's at least detecting them. So like really small tweaks like this can impact how well your model performs. So you can see that's tracking. Not too bad, right? Definitely improve it. If we come close, how are we looking? It's a little offset, but remember how we were taking a look at those annotations and they weren't quite on. I wonder if we could definitely improve that. I think if we were to go ahead, I'd probably go for, I don't know, like 300 epochs and see how that actually performs. But it's tracking. It's just like a little offset, which is kind of weird. Makes me think that the annotations were a little bit out, but I mean, at least you're seeing a real-time implementation and something from scratch, right? So I'm going to call this a win. We could definitely go and improve on it to go from here, but that's at least the beginnings of actually how to go on ahead and build an iris tracking model. All right, let me go and shut this camera down and work out how I'm going to reset the recording. Okay, so that is our iris tracking model now built. So you've at least seen the fundamentals of how to go about building this and at least seen a real-time test. I think in the future, what we'd probably do is add in a ton more and maybe just double check those annotations, because I think that maybe we could definitely have improved on what we had from there. But that's at least our initial model now built. Let me know what you thought. It probably definitely needs a bunch of improvement, but at least it's a beginning. And hopefully this helps you out if you are going to be doing some key point tracking. Thanks again for tuning in, guys. Peace.
Thanks so much for tuning in, guys. Hopefully you enjoyed this video. If you did, be sure to give it a big thumbs up, hit subscribe, and tick that bell, and let me know what you thought of this video in the comments below. If you want a video on how to actually build up your own data set yourself and how to actually annotate, let me know in the comments. More than happy to do a video for that. Otherwise, the code is in the description below via the GitHub link, so you can definitely take a look at that. Thanks again for tuning in, guys. Peace. Why you only babysitting 2 or 3 shots? Let me show you how to turn it up a notch. What am I doing?